introduce Daniel Sanchez. Daniel is a native of South Carolina. He did his undergraduate work at Lander University and got his bachelor's degree in biology. And he came here to work with Dr. Duncan on some very interesting pollutant issues. And he'll hopefully be finishing up his master's thesis this summer. So we're going to get a little bit of a preview here, as sometimes happens, before the work is completely done. And I've heard him talk a little bit about this at some of our soils research meetings. It's very interesting stuff. I'm sure you'll enjoy it today. And hopefully somewhere down the line, not too far down the line, Daniel thinks maybe he'll continue his doctorate studies as a doctoral degree somewhere as those things line up. Hopefully those pieces will fall into place soon. But anyway, it's our pleasure to hear today from Daniel. Looking forward to your presentation.
Thank you. Thank you, Dr. Ravenhorst. And thank you, everyone, for attending, both in person and online. I'm really excited to be able to talk about my project today. I also have to thank Dr. Duncan for advising me. The title of our project is Phytoscreening of PFAS near Fort George G. Meade. I'd like to start by showing an image. There are maybe two facts that really impressed on me the importance of this issue of PFAS contamination in the environment. The first is a map, and this map shows areas where PFAS has been confirmed in some environmental medium. Scarily enough, this is actually really doesn't scratch the surface because we know that it's far more widespread than just these areas. But this is a good first step in helping me to understand. And it also doesn't show just how global of a problem this is. Another fact is that approximately 98% of Americans have some amount of PFAS in their blood. When I heard about this, I felt like violated. How did I not know, what's in my own bloodstream? So we'll talk more about what PFAS are, how they are released into the environment, and how it fits within the context of my project. So PFAS is an acronym. It stands for per and polyfluoroalkyl substances. Importantly, it's not just one chemical, it's a class of chemicals. And they're quite diverse, as shown by this diagram. Many different forms that they come in. But they have a few things in common. But all PFAS have to contain, they're essentially defined as a highly fluorinated compound with at least one carbon group that has been completely fluorinated. So if you see here, I forget that there are people online. Well, they'll watch me walk to the camera. If you look here at this methyl carbon, that's completely fluorinated, that would make this compound a PFAS, essentially. And this carbon to fluorine bond is extremely important because it's the strongest bond in organic chemistry. And it makes these compounds really, really robust, very stable, both to chemical degradation and thermal degradation. And this has the unfortunate side effect also of making them quite persistent in the environment, which is why they're so widespread. And it's also why they're often called, you might hear them called forever chemicals. I chose to use this diagram because it shows a pattern that's common to a lot of PFAS, which is that they contain both a hydrophobic component and a hydrophilic component. And this is similar to how you could think of like soap. And it gives them a lot of unique physical and chemical properties that are useful for a lot of different applications. One of the most common examples that I can think of is non-stick cookware. And you can see a lot of other applications shown here among, in addition to those not shown. And beyond cookware, there are just many different examples. But the type of PFAS that are, at least the use of PFAS that I'll be highlighting today is firefighting foams, because these are one of the most relevant in terms of PFAS released into the environment. Sorry, I'm going to adjust my notes as well. So, talking about firefighting foams, or more specifically, aqueous film forming foams, are a great example of how PFAS are effective at doing their job, and in fact, probably too effective. So, aqueous film forming foams are used to extinguish Class B fires. These are fires that are fueled by really intense or very flammable, highly flammable liquids. So they burn at really intense heat. And whereas other chemicals might not be able to smother these fires as well because they'll break down, their high stability makes them resistant to breaking down and makes them effective at extinguishing these fires. Historically, AFFFs, or aqueous film forming foams, contain several long chain PFAS, like PFOS is a very common one, and PFOA. But in around the 90s, a lot of new data showed that these long chain compounds were showing toxic effects both to humans and wildlife, and that they were quite widespread. So these long chain compounds, being like around 6 or 8 carbon chains, were phased out for shorter chain compounds because these are thought to be less bioaccumulative and also less toxic. But though production of these legacy contaminants has decreased overall, the U.S. Department of Defense is currently doing investigations across the country, and their investigations in environmental media reveal just how widespread the problem of PFAS contamination is still today. So how does phytoscreening fit within this problem of PFAS contamination? Well, in any investigation, it's important to delineate the groundwater contamination to better understand the extent of the problem. Though this is most commonly done by digging wells, phytoscreening is an alternative application of aiding this process. The idea is that plants that have access to the water table have the potential to uptake contaminants as well and accumulate them within their tissues. And through sampling, we can gain a better understanding of the extent of contamination. More specifically, in practice, I keep doing it here and not realizing it's not doing here. I'm sorry. In practice, this looks something like this workflow, where a plant tissue is sampled. It's most commonly done in trees, and within trees, it's most commonly done on the tree trunk tissue specifically. This is one example of a method to do that with. This is an increment bore that I've shown here. It has thread like a screw at the end, and a tool that can be used to extract the tree core once it's been drilled into the tree. And this plant sample is then analyzed using some appropriate chemical techniques. And then this data is used to delineate the groundwater plume of contamination. And it's worth mentioning that in addition to evaluating this technique, another large motivator of this study was just to observe PFAS uptake in trees. By far, most of the studies that have looked at PFAS uptake in plants are focused on agriculture because that is an important pathway for humans to be exposed. So I can really only think of about 3 studies that look at PFAS uptake in trees. And to my knowledge, I think this might be the first to look at PFAS uptake in trees at or near an AFFF impacted site. So that's also worth mentioning, that another motivation for this study. But now let's talk about the research objectives. So the primary objective is just to evaluate whether phytoscreening is a viable method of detecting PFAS in groundwater. We selected as our point source Fort Meade. This is outlined in white and in this kind of pinkish hue. This is an area that this is a military base that has a history of AFFF use. And in 2020, the Department of Defense conducted an extensive investigation at many of these areas outlined here, where they sampled groundwater, soil, sediment, surface water. And so we chose to use it so that this groundwater data that's publicly available, so we could focus on the plant samples in that side of the project. Our second objective was to characterize the spatial variation of PFAS in proximity to a point source. A lot of evidence from the literature shows that PFAS can partition in environmental media based on their chemical properties. One that I've shown here is carbon chain length. This is, of course, just like a diagram, not necessarily trident. Yeah, this is like a conceptual diagram more than anything. But it shows how PFAS have the potential to partition. So we wanted to assess this by sampling from various proximities from the base. So this is the same map that I showed you before, and these are the 3 sample sites that we selected at varying proximities from the point source. And notably, we chose the first 2 as close as possible to groundwater well samples that were taken from the Department of Defense. The third objective is to compare between PFAS accumulation between species. These 3 species, red maple, willow oak or swamp willow oak, and sweet gum, were very common on the site. And because they were so common, we were able to have each species represented at each of the 3 sites. So this is a close-up of what I showed earlier, and I'm going to take the circle off so that you can see more specifically where we sampled trees and also where we took auger samples, which I'll talk about later. In total, there were 3 tree species at each site and 3 sites, so 9 trees in total, but more samples collected than those numbers. The final objective was to characterize the impact of the plant media that we're sampling. So if we were to sample the tree trunk, the tree branches, and the leaves, which media might have, or which tissue would have the highest concentrations? Lots of literature, again from agriculture, suggests that the highest concentrations tend to reside at the highest proportions or at the highest portions of the plant, so like the leaves, the vegetative components. But of course, trees are much larger than crops, so would this pattern hold up when tested? We did this by sampling first from the soil to get a better understanding again of this partitioning process. And we did that by sampling from 0 to 10 centimeters at the surface, normally about 45 inches from the base of the tree. We then sampled again using this increment bore that I talked about earlier from the trunk of the tree, and in line with an estimated line with the water conducting elements or the xylem of the tree. We took branch samples, and you can look at the base of this picture how this is an area that we would cut off and store for the sample, and then we would finally sample from the leaves of this branch, just really from all leaves of varying parts of it. And we also took auger samples, one at each site, just to gain a better understanding of the soils at each of these sites. Some I guess important traits or things to notice. Site 1 was quite sandy, probably very characteristic of the coastal plain physiographic region that we're in. Site 2 had a buried A horizon, indicating some human disturbance in the past. And you can see this by the really dark, stark line in the middle. And Site 3 had a high levels of organic matter all throughout, probably indicative of high moisture throughout the year. But we sampled at 30 and 40 centimeters, so 30 to 40 and then 100 to 110. It's really important to, when analyzing these compounds, to have a high fidelity to quality control, because these samples are being analyzed at just such low concentrations. Sorry, I just okay. I didn't know. I didn't want it to restart during. Yeah. So for instance, in our method, we were sampling at parts per billion. So everything from what we're wearing that day to our gear has to be just vetted and paid a lot of attention to, so that we're not bringing contamination. And furthermore, we have to be very careful when dealing with these samples and equipment to avoid cross-contamination. So that's Grace and Isabel, who are in this room. Thank you both. And this shows our decontamination procedure. So we had Alkanox, detergent, and tap in one bucket, then 2 tap water rinses, and then a third tap water rinse, or not tap water rinse, a third DI rinse with water that was shown to be free of PFAS before we took any sample. And sorry, before I move on, we also stored these samples on ice up until analysis, which came about a month later. So we chose to for our analytical method, we chose to use the EPA method 1633. You'll see that this is a draft method. The EPA currently does not have any published official standard for analyzing PFAS and environmental media, though they do for water and drinking water. We chose the method because, well, we had some collaborators at the EPA, so they were familiar with it, and we also it's also very well. It's also very thoroughly written out. We did make some modifications this to help our analysis be more streamlined. The modifications all should go to the credit of Chris Fuller, who's at EPA and Research Triangle Park. He demonstrated these modifications, which really accelerated the entire process, had no negative impacts on the analysis. The main one perhaps being the solid phase extraction pumps, which I can talk to those who are more interested in this later, but yeah, just really help streamline the process. Another thing worth noting on here are the EIS spikes, or the extracted internal standard spike and the non-extracted internal standard spike. These are considered the gold standard for PFAS analysis and quantitation, because you are essentially adding an isotopically labeled compound that behaves very similarly to the actual compound, and a non-isotopically labeled compound to both help to quantitate the PFAS levels in your sample, and also account for any PFAS that was lost during your extraction. Something else might be worth noting, or to interest of some, is that we used an LC tandem mass spec, and this was done again at EPA Research Triangle Park. So going back to our first research question, is phytoscreening a viable method of detecting PFAS in groundwater? Well, I've made this beautiful Venn diagram. I love a good Venn diagram. And it shows that many of the analytes that we detected in our plant samples, which were quite a distance away from the point source, had a large amount of overlap with the groundwater that had been detected 3 years prior. And interestingly, we detected an analyte, PFDODA, which was not detected in groundwater prior. I'm going to show, or I am showing, the total PFAS concentrations in groundwater 3 years prior to give you a better picture of what that looks like. Some important things to note are, I guess I'll start with the axes. So the y-axis is the cumulative concentration in nanograms per liter or parts per trillion. And these areas on the bottom are show the areas where groundwater wells were sampled at Fort Meade during that DOD investigation. You can perhaps recognize PFOS and PFOA, which I talked about earlier, as being legacy contaminants. You can see that they run throughout many of the samples and are still an important source in this mixture. However, there are other important compounds like these two precursors up here, which are compounds that have the potential to change into other PFAS, degrade into other PFAS, even legacy PFAS, and other compounds like PFHPA and PFHXA, which are a 7-carbon compound and a 6-carbon compound, respectively. I think the main takeaway from this graphic that I wanted to show you is that it's just showing the magnitude of difference between our samples and what was detected in groundwater. So here I said that they were in parts per trillion, and cumulatively might have added up to 4 parts per trillion. And on the next slide, I'll show that when averaged together in dry weight, our samples, or the plant samples in this data set, reached up to like 15 parts per billion in dry weight. This is dry weight, so it's going to amplify the concentration, but even when I accounted for percent moisture, this pattern is still seen that these compounds are present at a parts per billion magnitude, which is quite elevated. And yeah, I think that was a surprise to me as I was doing the analysis. I think this is indicative of bioaccumulation. According to the literature, the literature has shown that these compounds are able to remain in ecosystems or systems for a very long time, especially with in systems with high amounts of organic matter. So going back to the second research objective of characterizing the spatial variation of PFAS, I've chosen to use, instead of the average concentrations, the cumulative total PFAS concentrations in all plant samples across all 3 sites. This symbol right here, this 27, is just indicating that it's just indicating all of the analytes that we included within our study, 27. And again, these are showing all of the analytes detected. Another perhaps surprising fact is that Site 3, which was the farthest away, actually had some of the highest consistently detected concentrations of PFAS. And I'll dive into that because I'll first show this map. So as I said before, Site 3 is one of the farthest sites away from the fort, from the base. However, the chemical concentrations, so if you look at 6,2 FTS, is quite elevated at Site 3 and Site 2, and we believe that it's this detected analyte that is in common with the area sampled, number 6, which is, wow, I'm so sorry. I hope this makes sense. This area, okay, so this area, building 6691, that is the area, that is area number 6 shown on this graph. So this is the area that had some of the highest concentrations, and it's this analyte 62FTS that was in common with plant samples at site 3 that lead us to conclude that this site actually was influenced more by surface water than surface water than groundwater. So you can see that this area where it says current FGGN fire station is near to a stream, which is perhaps responsible for depositing these compounds at site 3 and not at site 1. Yeah, there it is. Wow. Okay. Yeah, so the next research objective was to identify whether there were differences in uptake between plant species. And the other one was to determine whether there was differences in uptake between plant tissues. So these were both analyzed at the same time using a linear mixed effects model. This shows, I think I'll probably come back to this, I'm sorry. This shows how that data was processed. We did this on the basis of individual analytes and on total PFAS, both by dry weight and wet weight to gain different insights. We also did this for soil, and unfortunately I won't be able to present on soil today, I think due to time. Yeah, we can talk more about the random effects that were incorporated if you're interested afterwards. But it's just a way to account for variation between the sites and replicates. So first I'd like to explain what's going on here. Each dot on here represents an estimate for each of these variables, or values for variables. So, and ones that fall on the right of 0 are considered to have a positive effect, whereas those that fall on the left are considered to have a negative effect. The lines, the horizontal lines, are a 95% confidence interval, and when they overlap with 0 are considered to not have had a strong effect, and when they are not overlapping with 0 are considered to have an effect. So from this data, we concluded that the species, at least for dry weight, did have an impact on total PFAS accumulation. And that's seen by the willow oak species and red maple that did not overlap with 0. And we concluded that because all plant parts overlap with 0, that they were not a significant contributor to, or they did not have a significant effect. And we can sort of see this on this plot here. I plotted species, and you can see that the magnitude of, there's a difference in concentrations between the sweet gum and willow oak and red maple, where willow oak and red maple just accumulated higher concentrations overall. And now for the wet weight data, again, the same rules apply, except in this case, the species did not have a significant effect, but the media did, specifically with the core accumulating the highest concentrations of total PFAS. And I've shown this here, where you can see the species again. It's the same plot as before. However, you can see that the core accounts for a high proportion of PFAS in these samples. So briefly, I will talk about how this compares to what is seen in the literature. I mentioned earlier that many of the studies have shown that PFAS tend to be higher concentrations, and the higher parts of the plant, so the vegetative components, and decrease at lower parts of the plants like the roots or the stems. This study showed the opposite, which was that concentrations were actually higher at the lower parts of the plant like the core and the stem. Another study that did PFAS uptake in trees found that both were true, and it depended on the species. So in the case of birch, the opposite effect was observed, and in the case of spruce, the same effect as ours was observed. Finally, I will say that of course, it's good to acknowledge the limitations. First, we were only able to sample once. This was, I didn't mention this earlier, but this was in July, and so this is one sampling event in a single week, whereas this could have been replicated either annually or throughout some sort of season. Also, the sample size is small compared to other studies. I mentioned that there were 9 total trees, and of course there were more samples from each of those trees, and there were also duplicates, which I forgot to mention earlier, but again, something that should be acknowledged. And finally, the detection limit, we weren't able to go as low as as those who are studying water perhaps may be able to go, simply because of our method. So some final conclusions are that PFAS are capable of detecting a variety of PFAS compounds, even at some distance from a point source, as we saw from that Venn diagram that I'm so proud of. Also, regarding phytoscreening, we saw that sampling from plants has the potential to reflect accumulated concentrations. Again, these were orders of magnitude higher than what was found in groundwater. And so this might even be useful to those who are not able to get their method detection limits low enough to be able to sample water samples. And finally, we believe that this method could be insightful for site assessment. I showed all of the composition from each of the sites, and that is the sort of information that is needed when trying to investigate the source of PFAS from different areas. So future directions, we are open, or at least the lab is open, to additional sampling at this, actually in this area. Of course, you could characterize the distribution of PFAS even within a given tissue to determine more mechanistically how these compounds are moving. And also the characterization of PFAS within the soil data still is left to be analyzed. So I'd like to acknowledge those on the screen, everyone who helped sample, and for everyone who advised me. Yeah, and thank you.
So we have time for some questions. I'm sure lots of you have questions. I want to mention, first of all, both to you sitting here and to those online, that there's an evaluation link that showed up in your email that we'd like for you to complete to let us know, give us some feedback on Daniel's seminar. And since I've got the floor, I'm going to ask the first question because I may not be able to get it in edgewise. But I'm wondering, Daniel, you talked a lot about sort of groundwater transport of PFAS. Has there been any documentation or measurement or attempts to measure atmospheric transport of PFAS compounds, like with rainfall collection and things like that? Is that a relatively minor input, or is there some reason to focus mainly on the groundwater?
Yeah, so you bring up a good point that there are many different sources of PFAS in the environment, and that there is some background level of PFAS in the environment. So to be able to distinguish between those sorts of processes and the input from a point source like Fort Meade is important. I would say for our study, that comes down to the magnitude of contamination. We did not, it's important to know that we did not choose a control site to incorporate that level of background information. But this, I would say that compared to the literature, these concentrations are unusual. We also measured, this is similar to your question, we also did measure rainwater because as we were collecting on these sites, it did rain. So we wanted to perhaps see if that would affect our results. And the rainwater, there wasn't any detected in the rainwater that we sampled. Yeah.
Was there anything unique about the forest structure at these different sites, like in terms of vegetative composition, like old versus new growth, or like was one site mostly like mature forest versus like saplings, or like a good intermix?
So I measured the age, or I measured the circumference of the trees so that I could later go back and estimate the age. I believe I haven't done that yet, but I can say that the circumferences were similar. As for anecdotally, the sites in terms of age seem the same. I will say the second site seemed to be more of an edge habitat rather than some of the other sites which were sampled more within the forest, deeper within the forest.
Thank you.
Mm-hmm. Yeah.
Do you think there's a possibility that all the PFAS at your site did not come from Fort Meade, instead came from the residential area to the southeast, or things of that nature, like any confounding spatial factors that might affect these results?
Yeah, I think that's a great question, and I believe that so I looked, when I was looking for groundwater well data, I found that there weren't many that were close to our sampling site. Maybe the closest was about a mile away. However, in looking at that data, I found that there was not PFAS detected in those residential areas. Yeah.
Do you have an idea of the size of your source? This is Bob Hill. The PFAS has been around since the mid-1930s. And as you know, it's labeled as a forever chemical by the National Research Council because nature doesn't have any way to break down the carbon-fluorine bond.
Mm-hmm.
So I'm sure the entire history of Fort Meade wasn't made available to you. So how do you know how big your source is? I'm sure there are sources other than just the foam you talked about. And so I'm just wondering about the size of your source of the PFAS. And, you have no way of knowing how many years it's been there, et cetera, et cetera, et cetera.
Yeah, that information was also published with the data regarding the site history, and I can say that for each of the sites that I showed earlier on the screen, they each have a different reason for being suspected of PFAS contamination. So the one that had the highest concentration was a current fire station, meaning that it has had fire trainings recently, which is probably why it has elevated concentrations. But there were other areas that were, this contamination was attributed to activities like a spill release, and in some cases they were attributed to cleaning the equipment. So not even the firefighting trainings themselves, but just decontaminating and rinsing the equipment off between use. Does that answer your question?
Well, no, it's just that, I'm sure they didn't make, I mean, PFAS that was used in the 1960s and 70s, 80s could still be there. And so that's why I was just curious about the extent and size of your source of PFAS.
When you say the size of the PFAS, could you explain what that?
Well,
What
no, I
you,
mean, it's just, you know, you, there can be sources of PFAS that you don't know about because if it was put down 50 years ago, it's still there or could potentially still be there.
mm-hmm.
And so I'm just curious about how you assess the size of how big your source is.
Oh, okay. Yeah, I mean, I would, let me think about that. Because that's also, I mean, that is definitely a concern for me as well when I'm analyzing this data, is how do I attribute, to what extent can I attribute the compounds that we are seeing here to those detected at the, in the groundwater? Um, I think, I think I'm okay with saying that I still have work left to do there. Yeah.
Okay, that's fine. I mean, there's a lot of different analytes you're seeing, so there could be multiple sources also.
hmm
So,
Yeah, I think evidence of that too is that analyte that I showed that was detected in plant tissue but not in groundwater. I think I would consider that background or just I would attribute that to some other source because it wasn't present at any of the sites that they sampled. Yeah, thank you for the question.
no, I was just curious how you had a handle on that.
Mm. Yeah.
I'll add a little bit of context to this, right? So we know the general scope of how PFAS have changed in the firefighting foams over the years, right? And it's relatively new information, but the profile, sort of the fingerprint, if you will, right? So when you identify 6,2-FTS, you got a new site, it's firefighting foams. It's the
Yeah.
same. When you've got PFHXS, that would be another that would be attributed to firefighting foam use. But it's important to remember all other processes of biodegradation and transformation and movement. Your signal is kind of going to be uniform PFOS, right? And so that is a background and a legacy combined signal, right? And you're not really going to be able to parse that. But we do know that at some of these sites, some of the larger PFAS have a tendency to stick to clays and other organic materials, right? So you can actually have a relatively spatially sort of peaky sort of identification of hotspots, basically, where what moves off would be that which is soluble or that which is a biodegradation product. So it'd be like 6,2-FTS moving and then becoming PFAS downstream. So, and then the other thing I was going to add that sort of helps you answer the question you just got, hopefully, because there's a bunch of work going on with that. The other thing I was going to add, 1633 became official like super recent. So yes, that's going to be the method for like NICD's permits. And things like
Okay,
that.
nice.
Yeah, so cutting edge stuff.
Yeah, so Dr. Hill, he mentioned a great point that the and actually I think you published some work on this that that's a good way to think about it is a fingerprint, and often these sites and these foams that they've been using do have a chemical fingerprint and a certain composition. I've also seen the literature, they will use like certain ratios of different chemicals to better get a grasp of that fingerprint. And so, yeah, that would be the step forward that I would use for my analysis too. Did you?
Yeah, I was curious about if you had any ideas about why the sweet gum had a lower concentration. Was it exposed to less, is it just taking up less, or maybe there's some kind of internal processes going on? The sweet gum wood is quite different from like maple and oak. Any thoughts about that?
I haven't looked into the physiological differences between the species, and yeah, I'd be curious to know that as well. Yeah, I mean, it can be attributed to site because it was present at all sites, and that was something I accounted for in my analysis. So yeah, I'm also interested in that. Mm-hmm.
Did you analyze any of the soil samples you had for PFAS, and were those related at all, like were between the differences between the sites? Like, did site 3 have higher levels of PFAS than site 1, for example?
Yeah, so yeah, that's another angle is to, because so the total PFAS across the soils was much higher than it was for the plants. This is, I think, evidence of, or at least like an example of what I talked about earlier and what he mentioned, that these compounds have a really high affinity for organic matter. So in surface soils especially, they'll linger for a very long time. It was similar to the patterns in plants in that the third site had the highest concentrations.
So is it, and those the compounds in the plant might have come from the surface soil and not from the site at all, right? From the firefighting site, unless it was a fingerprint, I guess.
Yeah, so
Did they take out from the soils versus they take out from the groundwater?
So if, I think there's two ways to think about it. If we are to assume that these are undisturbed sites, which demonstrated by the young growth is, might not be true, then if these are indeed undisturbed sites, that perhaps the only way that they could have reached such high concentrations is through leaf deposition, is my running hypothesis. So trees accessing these contaminants from the groundwater, accumulating them within their leaves, and then season after season depositing them, which could cause the high concentrations. Don't quote me on that. There's like no literature about PFAS that talks about that yet, or just at all. On the other hand, these sites could have, I haven't seen any evidence or any accounts of past AFFF use at these sites, but I'm not going to say that it's impossible. Yeah, so it could be that these, in that case, then the sites would be a leading contributor to their high levels. Mm-hmm.
We have time.
One last question from us.
Do you think that, I don't remember whether you said this, did you test that buried A horizon along with the top normal A horizon at that site? And did you see anything interesting there with that kind of lower down organic matter?
Yeah, I have not analyzed the soil. I think it's possible for us to do that as well. Yeah.
So those levels you were just talking about over here was referring to just the top,
Yeah, just the surface.
not those subsurface.
Right. Right. Yeah.
All right, well, before we thank Daniel one last time, remember that you have an evaluation link in your email. Be sure to follow up on that, and come down the hall and join us for a FMB. If you don't know what that is, ask your neighbor. And so thank you very much, Daniel.